Okay, so welcome everyone to the second part of the lectures on your lecture 4 about Fourier analysis and the Laplace operator. And so I'm going to complete somehow this progression of ideas that I started with in the first part, namely functional calculus, by going a little bit further into functional calculus and fractional powers. I promised you that there's going to be fractional Sobolev spaces, so that's for the first part of today. And then we're going to start building connections between functional calculus and Fourier analysis by means of two interesting examples. Okay, so just to recap what happened. So we convinced ourselves, and we proved actually, that minus delta, the Laplace operator, initially defined via sesquilinear form on H1, on Rn, so we're working on all of Rn. This operator was equivalent to a multiplication operator with a particular function m, sometimes called also the symbol of the Laplace operator, and this is 4 pi squared psi squared. Okay, so we had this commutative diagram that through the Fourier transform, the Laplace operator is unitarily equivalent to this multiplication operator. And we took benefit from this observation by getting a good idea of what f of minus Laplace operator should be when f is a function defined on positive real numbers. And the idea was that this operator f of minus delta would be defined by just taking this diagram and letting act f on m, because if you have a multiplication operator, then f of that multiplication operator should be the multiplication operator associated with the composition. Okay, and then we took this diagram that resulted as definition of f of minus delta. So it's the operator that through the same transform, the Fourier transform, becomes equivalent to this multiplication operator. Okay, and so that thing that gave us a map taking measurable functions on positive numbers to closed operators in L2. Okay, and we had the hope that this thing would behave as natural as it possibly can, in the sense that it will allow us still to do manipulation on the function side, and they would naturally translate into the corresponding manipulations on the operator side. Okay, and so this thing, this mapping, sending the function to the function with a variable replaced by the operator, is what we call the functional calculus. And we had one example that was very natural, so somehow we tested this construction by looking at integer powers of k, so k is an integer, and then we found out, okay, applying the operator k times just gives a multiplication operator with the m to the k, so the symbol becomes something up to a constant like psi to the 2k, and then the multiplication operator with the symbol psi to the 2k, with maximal domain in L2, even though we didn't call it like that, already appeared in the very first result of Monday's lecture, and it showed us that this thing with a graph norm is precisely the Sobolev space of order 2k. It was exactly the same thing. Okay, and so in particular, this operator is a closed operator, and so on and so forth. Okay. Now, if we already looked at power functions, the next interesting function would probably be to take f of t to be t to the alpha, where alpha positive is a fixed number. Okay, then this power function t to the alpha is a measurable function on the positive real numbers. And so we can associate it with it an operator. Okay? So the operator that you get, f of minus delta, I'm going to write more suggestively as minus delta to the alpha. Okay? And this is a fractional power of the Laplace operator. Okay? I mean, it is defined just through the functional calculus. And now what I want to do with it is I want to investigate these fractional powers. Okay? And a starting point is that I look at this result. Now, the order of things as they appeared in the lecture was that, of course, the Sobolev space was first, and then came the identification of the domain with the domain of minus delta to the 2k. Now, when I want k not to be an integer, but I want k to be a real number, then all of a sudden, the flow of idea has reversed, because on the left-hand side, we now know what happens if I replace k by a non-integer positive number. And I use, in analogy of this result, these fractional powers of the Laplace operator to define fractional Sobolev spaces. Okay? So, in other words, 4.11 definition, alpha is positive, I set h alpha r to the n to be the domain of minus delta to the alpha over 2. And I equip this space just with a graph norm. Okay, and this I call fractional Sobolev space. Fractional Sobolev space of order alpha. All right, that's a space I can come up with. It's going to be a Hilbert space if you use the graph norm correctly, because it's a closed operator. And so this is my fractional Sobolev space of order alpha. Now, this notation is consistent when alpha is an even integer. Okay, when alpha is an even integer, notation is consistent in the sense that this guy is still the Sobolev space as we always know it. Okay? It's also consistent if this alpha is an odd integer. In the sense that if alpha is an odd integer, say alpha is 1, then h1 already has a meaning from the chapter on Sobolev spaces. Now, is h1 the same as the domain of the square root of the Laplacian? Well, you use this result where we described h1 in terms of Fourier transform, and you remember that the symbol for h1 was just the absolute value of xi, which would be precisely up to a constant the symbol of the square root of the Laplacian, because if you take f as the square root function, then the symbol will be the square root of m, so this is also xi. So notation is also consistent for odd integers. So I didn't define anything new in the cases. I already knew my Sobolev spaces, but for all the fractional orders in between, I defined in a hopefully meaningful way a fractional order space. Now, stupid as it sounds at first sight, the result that you get for the odd integer alpha is equal to 1 is quite charming in a way, and I'm going to explain to you why. Okay, so the result that you get is called the Kato square root property. or just Kato property, 4 minus delta. And now what does this square root property say? Well, it says that the domain of square root of negative Laplacian is equal to h1. I already explained to you that this is going to be true. And moreover, if you think in terms of Fourier transforms, well, square root of Laplacian in L2 norm, I told you up to a constant, and the constant is 2 pi, so this is 2 pi times absolute value of xi in L2 when I take Fourier transforms, which is precisely the same thing that you would get if you take the gradient of u. Fourier transform has exactly the same symbol. When you take the absolute value of the symbol of the gradient, it's also going to be 2 pi times absolute value of xi. So you have this equality here. In fact, that is equal is not so interesting. The fact that it's comparable is more interesting because it adds a little more value to the fact that these two spaces agree as Banach spaces. But not only do they agree as Banach spaces, but also the homogeneous parts of the graph norms, that is to say, not the L2 norm, they're also comparable. Okay? And this works for all u in H1 of Rn. Okay, what's interesting about this proposition is when you think back where the operator came from, that it came from a sesquilinear form. And now the sesquilinear form that defined this Laplacian on Rn, what was its domain? The V in terms of lecture 2. It was an accretive sesquilinear form on H1. Right? So this H1 is the form domain. Right? So in this Gelfand triple story with the V and the H and the V star, or the V prime, the V was H1. And now we found out that the form domain is equal to the domain of the square root. And you're going to see later on that this Kato property persists through going to more and more general operators. Here it's rather clear, but it's the first time we see it, and we see that the form domain naturally reappears within the scale of fractional power domains, which is, if I wouldn't have explained it like this, was probably surprising. Okay? So this is a natural connection where fractional power domains appear when you study operators. Okay, one of the things that will keep us busy for longest time in the seminar is to see if we can do similar things for divergence form operators with coefficients on Rn. Or maybe with coefficients even on a domain or a subset of Rn. Okay. Do you have questions on that? Please. Okay, so the question is, does the graph norm of a power coincide with a Sobolev space for other powers? Right, I mean, for power 1 instead of power 1/2, it does. And if there's justice and there's a good rule, then the integer power Sobolev spaces appear as these domains. And because the Laplace operator actually does something to the function, it shouldn't be true that domains of fractional powers coincide with others unless the exponent is the same when I restrict to real exponents. Okay? But I'm going to answer a little bit further your question by showing you how I can describe these fractional Sobolev spaces without using the Laplace operator, but really in terms of functions. Maybe that's also the question that you were raising, because this H1 has a description in terms of functions taking u and a derivative. Now the question is, can I do something similar for fractional powers? And the answer is yes. And let me write down the result first, and then interpret it in a suitable way, hopefully. Okay, so I'm going to do the case that alpha is between 0 and 1. And I claim that the following is true. U is an H alpha function if and only if, well, U has to be L2, and the question is how much more does it have to be? And the answer is the following. So U is H is L1 Rn, and the following quantity has to be finite. What you do is you take something like a Hölder quotient, okay, this is things that you would look at for Hölder spaces. You take alpha, then you square the whole thing, and then, because we're still working in L2, there should be some L2 manipulation on this Hölder quotient, and the L2 manipulation that you do is you take L2 norm with respect to the two variables, and you integrate with respect to a particular measure that has a density that is not integrable along diagonal. Right? And so this is the same thing, and in addition, you get an equivalent norm by taking L2 norm plus this fractional norm. You turn it into a Hilbert space norm. This is an equivalent norm on H alpha. And you even have something that resembles a little bit this thing over here. Namely, there is a constant with the property that if you measure minus delta to the alpha over 2 in L2, this is up to a constant exactly the same thing as this fractional norm. Okay? And this works for all U in H alpha. Okay, and so you see that somehow these fractional Sobolev spaces between 0 and 1, they seem to fill the gap between L2 and H1 in a way that is a little bit in analogy with how Hölder spaces fill the gap between continuous and continuously differentiable functions. It's a very vague understanding, but this thing is something like an integrated Hölder quotient of order alpha. Okay, so there is no choice but to prove this result. Or you think, is it complicated, the proof? Does it answer your question, first of all? Or does it give a bit better feeling for what's going on here? Okay, very good. Okay, so this is purely a description of these domains on the level of functions. It tells you what this fractional Laplacian does on functions. Okay, so how are we going to prove that? It's not so difficult. Let's see. So you take a function in Rn, and you just start computing. So go for it. I could try to convince you that it's a natural computation by trying to do it off my head. Let's see if that works. So I start on the side, because I don't want a miracle to happen and all of a sudden this strange expression shows up. I go the other way around. I take the expression and I do calculations until I'm here. Okay, so I write out the expression, squared maybe, and if I square it, then this 1/2 is just gone. And now I want to do a substitution. Okay, I want to set y is equal to x minus h. Okay, and if I do that, then I get u of x minus u of x minus h squared h to the 2 alpha dx dh h to the n. It's just substitution. The good thing is that in this inner integral, all of a sudden, the h is something like a fixed thing, and I can think of this as translation of u. And now I'm using Plancherel's theorem, and I take Fourier transform of the inner thing. Now this inner thing is a L2 norm squared of a particular function, namely u minus its h translates divided by a constant. So if I do Plancherel, then this outer integral will just stay the same. So I copy that. And in this inner integral, well, I'm now integrating in the Fourier variable xi. And the expression that I'm getting is h to the 2 alpha, because that has nothing to do with xi. And then I get the L2 norm squared of the Fourier transform of this function. And the Fourier transform of this function is going to be u hat of xi for the first guy. And for the second guy, it's the Fourier transform of a translation. So it becomes a modulation. So I have to subtract off e to the minus 2 pi I xi times h. And all that is squared. Agree? Now that's pretty cool, because now you see that the whole contribution of u is just in this xi integral. So now I'm going to change order of integration again. And so I move the u hat out. So I'm getting integral on Rn. I'm getting u hat of xi squared, some monstrous term, and then I get a d xi. Okay, and at the end of the day, I want to compute the L2 norm of this. So if I use, well, there's a u missing. If I use Plancherel over there, has to be some integral of u hat times power of xi, and the power of xi should be absolute value of xi to the alpha. Okay, so now I have to just keep track of what is sitting inside of the integral. Oh, let me try to be more clever. Here, hopla. And anticipate some space where I want to put something. Okay, then I do d xi, and I put in the integral whatever there is. And so what is there is 1 minus e to the minus 2 pi I xi dot h squared divided by h to the 2 alpha dh over h to the n. Okay, that was just copy and pasting, moving all of the rubbish that still has an h into this h integral, and this good guy goes out. Now, the goal is to be at some point to be here. Okay, but if I want to be here, then I should have u hat, up to applying Plancherel's theorem, times absolute value of xi to the power alpha over 2 times 2 gives alpha, and then it's a L2 norm, so I should have 2 alpha as a power of xi. So let's just put it here, and let's divide it out here. Then also nothing has happened. Okay, and now there's not much choice that I have left. You see, I have to produce this constant over there. So I have to make this guy here a constant. So I call this I of psi and h. And now I have to prove that this I function is, this is a I, this is what? This is a function, this is just a function of psi. This whole thing is a function of psi, the h is the inner variable that is integrated away. Okay, so I have to prove that I of psi is constant. Now, note, first of all, I claim these I integrals. And when looking at these I integrals, let's just always assume that psi is in Rn, but it's not 0. Okay? And so this I of psi is finite, I claim. And why is this? Well, you have to see that this integral is finite. This dh over h to the n in n dimensions is precisely a power that is not integrable, neither at 0 nor at infinity. But if I look at this 1 minus 2 pi I psi times h, I can use the boundedness of the complex exponential and say that this guy is bounded by 2. And if I bound it by 2, then all of a sudden I am having a power of n plus 2 alpha, which is larger than n. So it's integrable for the large values of h. Okay, so the estimate by 1 helps me integrating for h large. For the small h, I have somehow find an additional decay power of h. But if I look at this function, as a function of h is a smooth function, it vanishes when h is equal to 0. So by Taylor's theorem around the origin, I'm getting a decay of this guy that is linear at least. So I'm able to control this by a linear quantity in h. And if I have a linear quantity in h, then I'm having power h squared here. I divide by h to the 2 alpha. 2 alpha is less than 2. So all of a sudden I get a positive power of h here, and then it's integrable also near the origin. Okay, so these two things together imply that these integrals are finite. Now, these integrals, they also have a fantastic transformation rule. Namely, if I look at r a real number, a positive number, and I scale my variable with r, so I replace psi by r psi, then what's happening? Well, if I replace psi by r psi, then this gives me rh here. It gives me rh here. So I can do substitution. Rh is equal to h prime. But then, because of integration with respect to this specific measure, nothing happens. Because dh over h to the n, then the functional determinant just goes away, and this is left invariant. Okay, so under this scaling, this I doesn't change. I can do something similar. I claim that if O in R to the n times n is an orthogonal matrix, then also this I doesn't change. Now, why is this? Well, imagine that I would plug in O psi instead of psi, so I get the O in here. I can put the O to the other side. Then I have like O transposed H, which is the same thing as H. And it's not the same thing as H. It's O transposed H, and then O transposed H would be sitting here. You substitute it away. You call it H prime. And once again, the integral doesn't change, because at all other occurrences, you take absolute values, and orthogonal transformation preserves distance to the origin. Okay, so under these two transformation laws, this function I is invariant. And that's very good news, because any vector in space, I can rotate it so that it's a multiple of the first unit vector, and then I can scale it so that it becomes the first unit vector. In other words, the combination of these two types of transformation can map any given vector to the first unit vector. Okay? So it follows that I of xi is the same as I of absolute value of xi times E1 is the same as I of E1. So it's constant. And the constant is not 0. Okay. So if it's constant and it's non-zero, then I can just call this thing star. And then I can continue. Star is equal to some constant times integral on Rn u hat of xi squared xi to the 2 alpha Well, this is the same thing by the functional calculus as minus delta up to some other constant, minus delta to the alpha over 2 u hat squared dxi. And then you use Plancherel, and you have the same constant, and you have the fractional power. Right? And then the proof is basically done. You have questions on the calculation, I guess. Questions? Not anymore. Great. Okay. So now this calculation that worked for every u in L2 without any additional thing. And this calculation is true regardless of whether u is in the Sobolev space or not. In other words, regardless of whether this quantity to begin and to end with was actually finite or not. And so all other claims follow from this, because now u is in H alpha precisely means that this guy is in L2, so it precisely means that this quantity here is finite, and vice versa. And in addition, this equality is already there. So by definition of these norms, this guy here is equivalent to putting the graph norm for minus delta to the alpha over 2. And this was the definition of H alpha. So from this calculation, everything else follows, and then proof is complete here, and I can stop. Okay, let's have a 10 minutes break, and then we resume with other stuff. What do I want to do next? Okay, so I showed you that these fractional powers of the Laplacian, they define a scale of spaces, and then the scale of spaces can be characterized purely on the level of functions without recursing again to the fractional Laplacian, which for my taste means that it's a natural definition and it's a good one, and it gives some intuition how these fractional powers interpolate between L2 and H1. Okay. Another thing that one could ask about this functional calculus is, in general, it takes measurable functions and it produces closed operators. Now the question is, under which conditions do I actually produce bounded operators? Okay. And so in order to avoid some discussions about measurability, I'm only giving an answer in the case that f is a continuous function. Okay, so suppose f on the open interval 0 infinity to c is a continuous function. And I want to answer the question, under which conditions is f of minus delta a bounded operator on L2? Okay, well, you know that f of minus delta is up to unitary equivalence through the Fourier transform is a multiplication operator. Right, so this operator corresponds to the multiplication operator with a function f composed with m. And at the same time, you know that the multiplication operator is bounded if and only if this multiplying function is bounded. And now, if f is continuous, then it's easy to check that f composed with m is a bounded function if and only if f itself is bounded. Just because this m function is surjective from Rn onto Rn without 0 onto this open interval. You can also do things when you merely work with measurable and essentially bounded functions, but then you have to worry a bit about measurability questions and null sets. Don't want to do that, okay? And it's not adding any further insight into our problem. So let's just stick with continuous, and then we can just write down what I said. This operator is bounded precisely when f is a bounded function. Okay, and in addition to that, I can say precisely what the operator norm in this case is. Namely, the operator norm of this is going to be the operator norm, because Fourier transform is isometric, by Plancherel. Operator norm is precisely the same thing as the operator norm of this multiplication operator, which is the essential soup of the multiplying function, which in this case is the same as the soup of f. Okay, so the operator norm is precisely the L infinity norm, or the infinity norm of f. If you want to view it in the fancy way, then it says that this map from continuous functions to bounded operators, this becomes some sort of a contraction, or even better. Okay, contraction is what we're going to see later on. But the important thing to keep in mind is bounded functions produce bounded operators and vice versa. Here it's easy because of the properties of multiplication operators. It's going to be much, much harder when we talk about more general operators later on. So later on we're going to call this a H infinity calculus, and it's going to be a property that is intriguing and hard to check, and it takes some time to develop all of the material. But here we see a first version of it, which comes from the theory of multiplication operators. Okay, so now I want to get some further insight into how Fourier analysis relates to functional calculus of the negative Laplacian in L2. Okay, so I'm going to talk about two properties in Fourier analysis. I'm going to prove them first using Fourier transform, and then we try to reinterpret them in terms of functional calculus. Okay, before we can do that, we just quickly recall that there's a thing like radial functions. Okay, so a function theta from Rn to C is called radial if it is invariant under all orthogonal transformations. Okay, so this is for all x in Rn and O in the orthogonal group on Rn. And you are going to be asked in the exercise, okay, and then if that works, if the function is radial, then you can play the same trick as in this proof. Then you can say, well, in this case, the value of the function doesn't change if I take any vector and I rotate it in a way that it becomes a multiple of, say, the first unit vector. Okay, so in this case, if it's radial, then this is the same as theta of absolute value of x times, say, the first unit vector. And then sometimes this is written as the radial profile. Okay, so there's going to be, what sort of letter do I want to use for that? In Tech, it's a var theta. Okay. Okay, so you can write it like this. There's a profile function on the real numbers, and you plug in absolute value of x, then it gives you back the theta of x. This is not so important. This observation is quite useful because, I mean, you already saw that it was useful in computing these fractional Sobolev norms. Okay, and then there's a fact that you're going to see in the exercises. Namely, if you look at radial Schwarz functions, then the Fourier transform maps radial Schwarz functions to radial Schwarz functions. Okay, you know that it maps Schwarz to Schwarz. The fact that radiality is preserved is something that you either know or you have to prove, but then because Darmstadt team happens to be the one furnishing the solutions, you guys sitting here have to actually prove it. It's not deep. Okay, and now I want to do something with these radial functions. All right. So let theta in Schwarz functions be radial. And now I have two results in Fourier analysis that more or less follow similar intuition. Namely, you're given a function u in L2 Rn, and you study its modified versions, and these formulas give possibilities of reconstructing u from the knowledge of these modifiers. Of course, you know when you can take a limit as t goes to 0, then you get back u by this approximation theorem. But at least if this theta is normalized to integral 1, but there could be other ways of reconstructing u from the knowledge of the modifiers. And I'm going to show you two results of this. Okay, so let's say reconstruct u from the modifier. Okay, that's going to be one thing. You can either reconstruct u or the L2 norm. One theorem actually gives a formula for u in terms of integrals over modifiers, and the other formula gives back the norm of u in L2. Okay. Sounds a little bit mysterious at this point. It's going to be much clearer when I write down the results. Okay, so this is 4.15 proposition, and this is called the reproducing formula. Okay, so the theta is always going to be a radial Schwarz function in what follows, and I make the additional assumption that the integral of theta is equal to 0. In other words, the Fourier transform of theta vanishes at the origin. Okay? And then the reproducing formula says that if I integrate these modified versions of u with respect to dt over t, and then you keep in mind these functions, this is L2 modified convolution with a Schwarz function. So this gives L2. And so this is a L2 valued integral. As a function in t, for every t, this is a L2 function. So this is an integral of a L2 valued function. It's the first time that we're seeing Bochner integrals in this course. And the reproducing formula says that if in this integral I take limits as epsilon goes to 0 and r goes to infinity, then this gives you back u up to a constant that depends on theta, and the constant is the integral 2 times the integral from 0 to infinity of theta hat of s E1 ds over s. So it's a numerical constant. In practice, you would normalize the function so that this thing gets 1, and then you get back precisely u. Okay? For some reason, I want to do the modification with the square root of t. You're going to see later on. But that doesn't really matter if you're integrating with respect to Haar measure. Okay. So the reproducing formula says that you can retrieve the function back from integrating the modifiers in the t direction. And then, before proving that, let's put face to face the square function norm. Square function norm says that under the same assumptions, you can compute up to a constant the L2 norm of u squared as, well, you do more or less the same thing. You take norms here, you pretend you could put the norms here, you even pretend that you could put the squares here. The thing works out, so you get the integral from 0 to infinity over theta squared of t convolution with u L2 norm squared dt over t. Right, so if you compute the norms of all these convolution guys in L2 and you make a square function out of it by integrating the square of the norm with respect to the auxiliary parameter t that describes the family, then you get back up to constant precisely u in L2, and the constant in this case is twice the integral from 0 to infinity of the radial profile squared ds over s. Okay. This reproducing formula says that you can write any L2 function as a vector-valued integral over smooth functions. This is going to be very helpful in the later lectures. You're going to see it reappearing when we prove properties about functional calculus. At this point, it's more a property of Fourier analysis, and we're going to use the Fourier transform to prove it. But then in the end of the lecture, we are going to reformulate these properties using functional calculus. Do you have questions on the statements as they stand? Please. Which one? This one over? The upper one. Yeah. There's a reason why I did not write 0 to infinity, but I wrote Bochner integrals on compact sets and then I took a limit. There's a reason. There's a reason for this. It's in general. The question was, for those who couldn't hear it, question was, is this in general improper integral? Yes, this is also a way of saying that here there's some sort of improper Bochner integral. Okay, when we're getting used to the fact that in these reproducing formulas, it's always in this sense, at some point I start writing 0 to infinity and I say, well, keep in mind that's an improper integral. Okay, and part of the statement, of course, is, in case that was the other question that was going to be asked, part of the statement is to convince oneself that this integral exists in the sense of Bochner. And because it's the first time that we see a Bochner integral, of course, I'm going to explain to you why the integral exists. Okay, so this is a L2 okay. In case you haven't looked into the appendix, we sort of warned you that the appendix is going to be used from lecture 4 onwards. We're not using too much properties of Bochner integrals here. Okay, so if you haven't looked it up yet, well, either you pause the video and you check quickly the results on Bochner integrals and make the link to what I'm going to say next. If you're sitting in Darmstadt and you have forgotten that Bochner integrals are going to show up in this 4th lecture, then we're probably sorry and we should have told you more clearly, but it will be enough to know for this lecture that a continuous function valued in L2 is Bochner integrable over compact set. Okay? And then you have to look up the Bochner integral for tomorrow and for next week. All right. Also, the language of Bochner integrals here, I should say, I'm using it here because this is what we're going to use in more general settings later on. I think strictly speaking, it would not be necessary to formulate the things like that. But it's this formulation that sort of extends to much more general operators. Okay, so let's try to prove it. And let's try to prove 415. You're going to see that 415 is the hard one, whereas 416 is much easier. Okay, so what should one do? Maybe start with some preliminaries. Making sure that all of the objects that show up in this statement actually make sense. All right, so the first thing that you should convince yourself of is that this integral with a theta hat, this integral exists. Now, why is this? Well, if I look at the Fourier transform of theta, this is a Schwarz function. Okay? So if I want to see that this real integral over here defining C1 of theta exists as an honest Lebesgue integral, then I need some decay at infinity, but theta hat is a Schwarz function, so it has as much polynomial decay as I want. So just to say that theta hat is bounded by constant times, say xi to the minus 1, this would give you a decay of 1 over s for the function that you're integrating in, and then you're 1 over s squared. You can integrate when s is large. All right, so this estimate takes care of the integral, say, from 1 to infinity in s. All right, I'm always talking about this integral here, the scalar one. At the origin, well, you're integrating ds over s. You need to find some decay as s goes to 0 towards 0. And this is where the assumption kicks in, because this Schwarz function is a nice function around the origin. It vanishes at the origin. So for small values of absolute value of xi, you will have linear control over this function. Just because it's smooth and it vanishes at the origin. And then for small s, you see that over there, the function you're trying to integrate is controlled by constant times s, and you can integrate with respect to ds over s. Okay, so this says that the integral defining c1 of theta is okay. In other words, integral theta hat s1, this is finite. Okay, and I call this, I have to keep up with the numbers in the lecture notes because we're going to use these properties all the time. We call this 4.6. Okay, this is one preliminary thing. So the next preliminary thing is to make sure that these Bochner integrals over the compact intervals from epsilon to r, that these functions are Bochner integrable. Okay, and then there's a result in the appendix saying that if you have a continuous function, then this vector valued integral is well defined. And so I'm claiming that the function f going from 0 infinity to L2 of Rn, that this function is continuous. If this function is continuous, then this vector valued integral is defined. Okay, I think there's a ton of ways, and all have their own charm and reason to prove that this function is continuous, but because we're going to use the Fourier transform anyway later on, let's let's do it. I should say what's the function here? Otherwise, the statement is kind of weird, is it? So f of t should be what I want to integrate. So theta square root of t times u. Okay, this function should be continuous, and I want to say the vector value integral exists because the Fourier transform is a isomorphism on L2. Having continuity of this thing is just as good as looking at Fourier transform of f, where this f Fourier transform is the Fourier transform on this space. So it's pointwise for every t, and then I have to prove that the Fourier transform of this whole thing, this is a continuous function valued in L2. That's the same thing. Okay, but now what's the Fourier transform? Of the function that I'm trying to integrate? Well, Fourier transform of convolution means product of the Fourier transforms. Okay, so this is product of the Fourier transforms, so it's going to give us a u hat. And maybe I want to calculate at some position xi. Then it gives me u hat of xi. And then I have to take the Fourier transform of the modifier attached to theta. And this was one way of formulating the rule for Fourier transform in dilations, was that if I take the modifier associated to a function and I take Fourier transform, then this is giving me Fourier transform at the function where I multiply by the modifier variable. Okay, and then I use the fact that the Fourier transform is radial. So this is the same as theta hat square root of t absolute value of xi e1 times u hat of xi. Okay, now I want to prove that this is a continuous function of the variable t valued in L2. Now, in order to do that, you see this is a L2 function and I'm multiplying by stuff. If the stuff I'm multiplying with is uniformly bounded and it depends continuously on the variable t for almost every xi, then I can use dominated convergence and get continuity valued in L2. And clearly, this Fourier transform of theta, this is continuous, this is bounded because it's a Schwarz function, and it's continuous with respect to t. Okay. And so this continuous variation of the prefactor of u, if this is bounded, you use dominated convergence, you get the continuity for the L2 topology. And so therefore, this expression shows that this function over there is indeed continuous, and hence the integral makes sense. Okay. So now I want to do, what do I have to do? I have to compute this integral. There's no way. So I have to show you how I compute this integral that's in the statement, and I'm going to do it on the Fourier side first. Okay, and then there's going to be some technicalities. So let's leave some space right here, and we're going to fiddle in the technicalities that we need to make the argument work, and try first to see what we can actually calculate. Okay, so I want to start like this. Epsilon of r, Fourier transform of f at t dt over t. And somehow I want to do computation rules for real integrals, not vector valued integrals, honest Lebesgue or Riemann integrals. And so I want to evaluate this integral at xi. Okay, let's pretend for the moment that I could put the evaluation of this integral inside. Just keep in mind, this is a vector valued integral, so the outcome of the integral is a function that has some external variable xi. But all of these guys for fixed t, they are also functions of the variable xi. So I could try to see if I can put the variable inside. Okay, and I put a question mark here to remind myself that I have not fully justified that this works. But suppose I did. Okay, and you see in the appendix there's a rule that says you can pull out linear operators from Bochner integrals. So that has to be useful at some point. Now if I would be able to do that, then I can use this formula down there, and I wanted to give it a name for reference, I guess. So we call that 4.8. So then I could use this 4.8 and I could write out the thing. So that would be theta of square root of t xi absolute value E1 times u hat of xi dt over t. Okay, and that's a good thing because u hat of xi is independent of t, so it would go out. And this is precisely what I gain if I'm able to move this exterior variable inside, then somehow I'm able to decouple the action of u and theta hat. So the u xi goes out. I do change of variables, setting square root of t xi equal to s. Okay, and at this point I'm using the radiality because I couldn't do this as a transformation for integrals on an interval if this xi would be a vector. But because the dependence is only on the absolute value of xi, I can smuggle the whole dependence of xi into the bounds of this integral. Okay, then you do the calculation, dt over t is 2 ds over s. You believe me on that, I hope. So you get square root of epsilon times absolute value of xi, square root of r, absolute value of xi, and then it's just theta of s E1 ds over s, and then it's u hat of xi. Okay, and now if this is true for every xi, then I can look just at this thing and at this thing, and then the xi variable is not important for the thing, so it's an identity of function. The L2 valued integral would be equal to this function. Okay, and then you can believe that there's a way of passing to the limit as epsilon and epsilon r, because the whole dependence is just in this multiplying function. So this expression here looks a lot like this expression where continuity and limits just follow from dominated convergence. All right, and so that looks okay as a roadmap. Now we have to just make sure that we can actually do what we're trying to do here. Okay, and so in order to justify this calculation, let me remark that if I want to prove that this yellow thing is equal to this yellow thing, and you completely forget about all the steps I couldn't justify in getting there. If I just want to prove that this is equal to this, then it's enough to do that, not for every u in L2. It's okay to do it in a dense subspace for u hat. Because clearly this is just a fixed function, it's bounded by the observation that this full integral, even from 0 to infinity, is bounded, which is over here. Okay, so this is a bounded function. And this is u hat. Well, this obviously depends continuously with respect to L2 norm on u hat. And at the same time, if you look at this function, it looks like this. This expression also depends continuously on u hat if you measure u hat in L2. And so if you have continuous dependence on u hat for this, you can use dominated convergence, and you get that this expression as well depends continuously on u hat. Okay, so my goal is to prove that these two things are equal, and it's enough to do that for u hat in a dense subset of L2. Right? If you don't see it immediately, it's a beautiful exercise to write out on your own, because there's different ways of continuous dependence. There's the continuous dependence on T, but there's also continuous dependence on u hat. You see from that, but all of the quantities depend continuously on u hat, so I can choose the u hat in a nice way if I want. Okay, and I'm going to pick them in a nice way so that I can do the dubious calculation without having to worry about the question mark. Okay, and so what I'm going to do is I pick u hat continuous with support of u hat. I'm going to call it K compact. Yes, please. Mm-hmm.
Under the condition that what we still show is actually the case, right? So we sort of the argument.
Yes. Yes. So I have to cook up. The question is, what does it actually mean, what I did here? If I can sort of reformulate what you're saying, I have to cook up enough good functions u hat such that this calculation would actually work. But if I manage to make the calculation work for a dense subspace of L2 for these Fourier transforms, then I get the end result for every u in L2 without being sure that the intermediate steps also work for these other guys. That's the thing. And so now I pick u hat in a way that its Fourier transform is continuous and compactly supported. And this is a dense subspace of L2 because CC infinity is dense in L2. All right? So we take inverse Fourier transform of CC infinity functions. And now what happens is that this function, Fourier transform of f, this all of a sudden becomes continuous if I consider it to be a function mapping in a smaller space, and the space I'm going to call X. X is all functions continuous on Rn with support in K. Okay? Because if u hat is supported in K, then all these functions are supported in K. And this map becomes a continuous map from 0 infinity into the Banach space of continuous functions on Rn that vanish outside of this set K. This becomes a Banach space for supremum norm. This map becomes continuous by some uniform continuity argument. And continuous functions that vanish outside of K with supremum norm, this is injected into L2. Okay. So I can just reinterpret for this u hat, I can reinterpret this map as mapping not into L2 directly, but into this space X. Space X, by the way, is beautiful. I didn't think about it when I wrote it. Okay, but so we go continuously into space X. Why is that useful? Well, space X carries supremum norm. So evaluating a function in space X at a position xi is a bounded functional from X into complex numbers. And now you look at this first space. Well, this was a Bochner integral valued in L2, but because the function is actually continuous with values in the smaller space, there's some consistency property of the Bochner integral that says that I can equivalently look at this as a x-valued Bochner integral instead of L2. And then there's a second property of Bochner integrals that says I can pull out linear operators from the Bochner integral. And one particular linear operator that you can pull in and out on the space X is the evaluation of a function at position psi. So the point evaluation, you view it as a functional acting on the x-valued integral. Operator goes inside, the question mark disappears, then I'm here, the rest was just real analysis. And so therefore, for these functions, it works. And then it works in general. It's a twisty argument. But when you're getting used to the Bochner integrals, you're going to see a lot of these arguments. Now, let's have a look at the end of the proof. Okay, because I have to worry a bit about time. Well, okay, that's just perfect. But I shouldn't spend too much time now on these things. But okay, I want to make it very clear that there's a trick, and you can always apply, if you have an x-valued Bochner integral and you have a linear operator going from x to some other space, then this operator can be commuted with the Bochner integral. And this is what I'm doing here. It's just a, at first sight, strange way to think of this point evaluation. Okay, now let's take this formula. It's now valid for every u in L2, even though the way of getting there was not valued for every u in L2. So, I have this beautiful integral, and I'm going to give a name to these integrals showing up here. Okay, so these guys here, oops, these guys I'm going to call I epsilon r of psi. Okay, and then I know that this thing here, this is I epsilon r of I epsilon r times u hat, okay, on the level of functions. Now, you see, I epsilon r is bounded as a function of psi, because if I take absolute value here, I can put the absolute value inside, then I'm integrating something positive. It cannot get bigger than integrating from 0 to infinity, but even integrating from 0 to infinity gives a finite number. So these I epsilon functions, they are bounded by this constant. Because they are bounded by this constant, it means that the integral here from 0 to infinity exists. So if I fix any non-zero psi, and I take the limit as epsilon goes to 0 and r goes to infinity, these functions of psi, they just tend to the value of the integral from 0 to infinity, which is by definition over there the number c1 of theta. Okay, so this thing here, as epsilon goes to 0 and r goes to infinity, this goes to c1 of theta times u hat in L2. Now, this is not precisely what I want, because I didn't want to have the Fourier transform inside. Okay, but I can apply Fourier transform here, or Fourier inverse. I can apply Fourier inverse here. Because there's a L2 limit, I can apply Fourier inverse here. So then this is just u. Then all I wrote is still true, but then because this is an L2 valued Bochner integral, Fourier transform is bounded on L2. It goes in and out of the integral. So this Fourier transform can go in here, and then it cancels this one. And then you see the integrals of this f of t function go precisely to that thing, and that's exactly the statement if you recall what f of t was, namely these modifications. So at this point, the proof is complete. Okay. Questions? At which point would it fail? Well, I don't know how to control. I just don't know how to control the thing, because this integral it's something like a integral of a derivative that in some sense calculated using fundamental theorem of calculus. And if there's, I wouldn't know, and you cannot justify that this integral converges absolutely if the norm is inside. There's no reason to believe, because if you put the norm inside, this function has a limit. It goes to u in L2. So if the norm would be sitting inside, this function would be continuous all the way down to 0 with a non-zero limit. And so it will not be integrable with respect to the measure dt over t. Unless you use this information, right? Use this information that the integral of this mollifying guy is 0. So in this case, the limit at t goes to 0 will be 0, and then there's some cancellation going on, but in order to see the cancellation, you cannot have norms. Okay, let's see. Proof of 416. 416 is the square function norm. I claim it's much easier, okay? Because integral of the mollified guy 2 norms squared dt over t. You use Plancherel because it's L2 norm squared, and you use the formula for the Fourier transform that is just sitting on the board here. So you get integral on Rn, you get theta hat of square root of t, absolute value of psi e1 squared, u hat of psi squared, d psi dt over t. Okay, now you have to do the same steps as you did over there, so that u hat has to go out of the integral. I can do that by doing it the other way around. So I do dt over t first, and then I do d psi. If I do it in this order, then this guy can be put out of the integral, and once it's out, I do the substitution again. I set s is equal to, well, then this integral, sorry, the integral has to be inside, otherwise my writing is nonsense. I did Tonelli, and then you look at this integral, you set s is equal to square root of t times absolute value of psi. You get the Rn integral. Now there's no epsilons in R, so it's going to be 0 infinity straight. It's going to be theta hat of s e1 squared. Harm measure is nice with respect to the transformation. It just costs a factor of 2. And then all this is sitting here, and u hat of psi squared was still there. And then you see I'm already done, because this is what I called C2 of theta. So it's just C2 of theta times what's remaining is the L2 norm of u hat squared, but then you do Plancherel backwards. You can kill the Fourier transform here. And then you see that this square function is just exactly the constant I claimed times u in L2. That was relatively easy because there was no cancellation going on in this. It's just a straightforward calculation using integrals. And also there's no vector valued integrals. I did the proof, so there it is. Okay, so I have 5 more minutes. And I need to tell you one of the most important insights from these calculations. So let me see that I get there. Okay, the proof, forget about it. And by the way, we're going to offer a different proof for Calderon reproducing formula in a much more general context using functional calculus. And then at some point you will compare the two proofs and you will see that, some of the technicalities I did here, they disappear from the proof in the more abstract framework. Okay, now what I want to do in these last 5 minutes is to change perspectives. Perspective. And I want to change perspective in the following sense. I want to understand these two results standing over there, not in terms of the Fourier transform and modifiers, but I want to understand it in terms of functional calculus. And I want to show you what they become if I use functional calculus. Okay, and so to this end, I start with a Schwarz function on the real line, and I suppose that f of 0 is 0. Okay, and if I have a Schwarz function on the real line, then I can define a new function, phi of xi to be f of 4 pi squared, absolute value of xi squared. Now you see where this is going. This phi is now a function on Rn, and it's believable, but it has to be proved as one of the exercises, that this is a Schwarz function on Rn. Okay? This is one of the exercises. Okay, and then, which is the function that I want to apply these results to? Well, you see, phi of 0 is f of 0 is 0. But these results require vanishing at the origin for the Fourier transform. So the function that I should be using here is the inverse Fourier transform, or the Fourier transform, or the inverse Fourier transform of phi. So let's set theta to be the Fourier transform of phi. And then this function, it is admissible in 415 and 416. Right? Because it's a Schwarz function as a Fourier transform of a Schwarz function, and the Fourier transform of theta is nothing else but phi at 0, and so it vanishes. So this guy is admissible. Okay. And the observation is now, what are these integrals that I'm looking at when I write the reproducing formula? Okay, so for example, this guy, this is the inverse Fourier transform of its own Fourier transform. And I'm saying that, okay, I erased it, but you remember that we calculated the Fourier transform of this. Okay, and the Fourier transform was theta hat of square root of t xi e1 times u hat of xi. Okay, but theta hat is the same as phi. It's phi, but then because of radiality, I can just put phi. And now phi at square root of t, absolute value of xi e1, you use the definition of phi, you plug this guy in, then you see I get Fourier inverse of f of 4 pi squared, because it has always been there. Norm of E1 is 1. I get t square root of xi, the absolute value, and then I get u hat. Okay, now this is Fourier transform multiplication, Fourier inverse, and multiplication is by a function that is composition of a function on the real line with this m function that corresponds to the Laplacian. So in other words, this is nothing else but f of minus t delta applied to u. Okay, and if I view it in this way, then 4.17, last corollary for today, is now the reproducing formula says that I find u by integrating from 0 to infinity up to the technicality of being improper as an integral, f of minus t delta u, and I get the norm of u squared by evaluating up to a constant. Now this could be constant of f. I get the norm of u squared by looking at these operators f of minus t Laplacian, taking their norm in L2 squared, integrating dt over t from 0 to infinity. Okay? And so in this sense, these properties and many others in Fourier analysis, they can be understood as particular properties of the functional calculus for the Laplacian. Okay, so there's two different perspectives. And now, similar to how I use the functional calculus to define fractional Sobolev spaces, if I want to imagine I want to work with a more general sectorial operator instead of this very specific operator minus delta on Rn. For sectorial operator, we will see that we can make sense of the functional calculus for a good amount of classes of functions f. And then we will be able to prove things like the reproducing formula and the square function estimates in terms of the functional calculus. Okay? So because functional calculus is going to be the topic from next week on for 5, 6, 7, 8, 4 lectures, what you should keep in mind is that it's an attempt, and it's going to be a successful attempt, of assigning to a more general sectorial operator something that plays a little bit the role of Fourier analysis. So think of it as a Fourier analysis adapted to a different operator, inspired by the fact that these results from Fourier analysis can be reformulated in terms of functional calculus for the Laplacian. Now, before I stop, I should just tell you that these constants, of course, you can compute, and so it's going to be the integral from 0 to infinity f of s ds over s, and the C2 constant is going to be the square integral. And no, I didn't forget the factors of 2. They go away because of square roots and squares and half measure. It's just minor things. The important thing is sitting here. You know how reproducing of a function and its norm works through the functional calculus. Okay. I stop here. Of course, you can still ask you can ask questions if you want. Maybe it's interesting. Participants online, they are not restricted to the schedule. So is there a question you wanna ask here? Just go ahead. And if not, then we have some, I hope, nice exercises for you. I hope you're going to discuss them in the discussion forum. I'm going to be off from the internet seminar, at least in the lecture hall, for at least 3 weeks. Robert has to work hard for lectures 5 and 6. Then maybe we're going to have a guest star for lecture 7. I'm about to convince yet another guest star to do lecture 8 for me. And then I just need someone to write lecture 9 for me, and it's going to be a very nice Christmas time. Okay, see you around.